Hey everybody, and this video today that I have for us is a good one. I think it's an interesting, at least for me, it's one of my favorite areas to study, and that is the nervous system. And we are going to think about and apply some calculus on a model developed for neural pathways, or a nerve pathway. And as an example, I don't know if this model doesn't necessarily relate to this given pathway, but it's a model that was developed in a long time ago, and it's published in the Mathematical Biology of Social Behavior from the University of Chicago Press, and it's on page 7, and here's a link to it. And I'll leave a link in the description because I know you guys can't click this, obviously. But here's our model right down here, and this model represents a pathway, and the pathway I've chosen to explain is the optic pathway, and it relates to the central nervous system and vision. And so when our eyes capture light data, that light data hits the retina, and that retina goes through various different subcomponents, and it's quite complex, but I'm going to keep it pretty high level. That data, after it hits the retina, is sent to the optic nerve, which is this big guy right here and this big guy right here. And that optic nerve takes that data and puts it through this central point called the optic chiasm. And this optic chiasm then pushes that data along to the other side of the brain, down the optic tract, and then that data is sent through various different other parts of the brain where it finally hits its final destination, where it's synthesized, and you're able to visualize information. You're able to visualize what your retina captured from the light and make a picture out of it. Your brain does an immense amount of processing to make that picture. For example, you're able to see this image on my screen right now. And so here's another picture of it right here. You can see that these are the optic nerves. It hits the chiasm, and then that data enters the optic tract where it's brought back to the brain for synthesis. And so this is really cool, and scientists were able to develop a mathematical model to explain a general explanation of how a stimulus will cause neural pathways to activate. And so we have defined our variables here, where I is our left side of the equation, which is the intensity of excitation. And the rest of the equation will equal the intensity of excitation. Our capital E here is the max excitation that the pathway can experience. Our S, which is right here, is our stimulus, the external stimulus, S. And then H is the threshold. So S minus H is, if S is less than or equal to H, this becomes 0 and nothing happens really. And so that's a threshold. And then A is just a constant, a universal constant depending on where the pathway is. And so we have our model here. Maybe we can apply some calculus and find the rate of change with respect to, the stimulus. So we can differentiate this model, or find the derivative with respect to the stimulus. So we want to know how the intensity of excitation changes with a change in stimulus if we keep everything else constant. I hope that makes sense. And so let's find the derivative of this equation with respect to S. So I'll rewrite this. We'll have the derivative of I with respect to S equal to the derivative with respect to S of E. Let's make this more like that. E bracket 1 minus Euler's number raised to the negative A times our threshold SH, all divided by our max excitation. Bracket and parenthesis. And so we want to find the derivative, like I've said multiple times now, of this portion. And so to do that, we apply some calculus. And what do we get? Well, we get the derivative of this portion. So the e is just a constant, so we can just leave that to the side. We can apply the constant rule for derivatives. Let's use a different color. So this e can be taken out. And so we have e. The derivative of 1, our term 1 here, is going to be nothing. It's just a constant. So that goes to 0, really. And so we have e times, now we have this part, e raised to this business right here. And this, we just apply our exponent properties. And so we could think about this as e times the derivative of EU. Let's rewrite this. E times the derivative with respect to s of EU times the derivative of s, I can write that better, derivative with respect to s of u. And I don't know if you guys recognize this, but this looks like the chain rule. This looks like the chain rule to me. And so what do we get? Well, we get, this is going to be equal to e times the derivative of EU is just EU, and the derivative of u is the derivative of negative a times s minus h divided by e. And so that's confusing, but we can make it easier, I think, on ourselves. Let's rewrite this over here. Okay. So we get times. All right, this business right here. So it's like negative a, and then our variable is our s. So this is like, you could imagine if you were, when you're practicing your calculus, is like the x minus a constant. So like x minus, it could be any number, like 3. And so what's the derivative of x minus 3? Well, it's just going to be 1, right? Because you're going to apply your exponent properties, or I'm sorry, your power rule for the x, which is x to the 1. And so you bring the 1. And so you really just got 1 over our e, 1 over our capital E. And so this is really times negative a over capital E. And this is our derivative. But I think we can write this a little bit cleaner. And so we get E times oh, by the way, this is negative because we have 1 minus e. So this is a negative right here, times a negative e to the u. So e times a negative a times e times a negative e to the u. And this a has an e right here, so these e's cancel out. Then we get 2 negatives times each other, which is a positive. So we get a to the e raised to the u. And so a times e to the u, that is going to be a e times negative a times s minus h divided by e. And so there you have it. This is the derivative with respect to s of our original function. Our original function up here. So this this right here is the derivative right here. So this is I of S. I prime of S is equal to that guy. It's equal to this guy. And so we could plug in any number of data endpoints, input data points for S, and we can find the rate at which the intensity of the excitation is changing for that given data endpoint. And so based on how much stimulus we are putting into the system of that, and the system in this case is a specific nerve pathway, and I don't know, it doesn't explicitly say what nerve pathway, but we could say that that nerve pathway was an optic nerve pathway. And so depending on how much light hits the retina, this is how much that would be the stimulus. We could plug that input in for us, and we get the level of intensity of excitation and that rate at which that intensity is increasing or decreasing, depending on what the model outputs. And so I thought that was a cool one. This is a very interesting subject for me. And so that's it, and we'll see you in the next video.